In a recent video, I explained that a single person falls at a different speed compared to two people jumping together, such as in tandem parachuting. Thousands of people literally jumped down my throat saying they had no idea about physics. I have two water jugs with me. One is empty and the other is full. What is your question? Do you think they will fall at the same time, or will the full one fall first? Surprisingly, both answers are incorrect, and I'm going to explain why. On Earth, all objects with mass experience the force of their own weight due to the acceleration of gravity. And we all know that this value is roughly 9.81 meters per second squared on the Earth's surface. This means that if we drop an object, it will not fall at a constant speed. It will accelerate more and more, that is, its speed will increase. This animation simulates an altitude of 196 feet from the highest to the lowest line. The intermediate lines are 20 meters apart. This is what would happen if a ball is dropped. Notice that it takes much less time to cover the last 20 meters than to cover the first 20. This is because the object is going much faster at the end. For comparison, I'll also demonstrate a ball falling on Mars and the Moon, so you can see how it differs from Earth. About 2,300 years ago, Aristotle stated that a heavier object would fall faster than a lighter one. As one of the greatest thinkers of the time, people didn't doubt him. I suppose that since a heavier object generates more downward force, when holding them in your hand, it made sense to think that the one generating more force would fall faster. This thought was respected until Galileo arrived in the 16th century and debunked it, saying mass didn't matter at all. The mass that the objects had, they would all fall with the same acceleration, that of gravity. Stories are told that he climbed the Tower of Pisa and dropped two objects of different masses at the same time to demonstrate that they would take the same time to reach the ground. As the story goes, this experiment worked, although there are doubts that it happened, but it is clear that whether through this experiment or others, Galileo made it clear. Before we continue, consider this. How can two objects of different weights fall at the same rate? The downward force is greater. Shouldn't the acceleration also be greater? No, because yes, the force is greater, but the mass is also greater, so it will have more inertia and therefore it will take more to accelerate. That's why in the end, it takes the same time to reach the ground. But the thing is, there's a problem. This theory of Galileo that I just mentioned in reality is not correct. Because in the world we live in, there is friction with the air, and that radically changes everything. I remember in school I used to think that the force of friction wouldn't really change the physics of bodies that much, but the reality is that it does. Here we have a feather and a ball. We know from our own experience that the ball will fall first, indeed. But it turns out that this experiment was being conducted in a vacuum chamber, so they could then remove all the air from the room. In this way, they would eliminate the friction with the air, and look what happens. Both objects, under these circumstances, fall exactly at the same time, governed by a constant acceleration movement. As Galileo said, regardless of the mass, both objects fall at the same time. But that only applies in a vacuum. For example, this experiment was also carried out on the Moon by the astronauts of the Apollo 15 mission, dropping a hammer and a feather at the same time. On the Moon, with no atmosphere, objects fell simultaneously. Air friction on a body is determined by a specific formula, where we see that the air density appears, the speed at which the object moves, the cross-sectional area, and the resistance coefficients. The air density appears in the formula because the denser it is, the more air the moving object will be colliding with. Interestingly, for example, a missile launched at sea level has roughly half the range of that same missile if it were launched from 10 kilometers in altitude, because the density at sea level is much greater and therefore slows down the missile much more. We can also see in the equation that speed appears. This is because the faster the body moves, the more air mass it will be affecting per second. When driving fast, more air hits your hand if you extend it out the window than when driving slow. But be very careful because the speed is squared, so it is actually the most important factor in this equation. The cross-sectional area is in the equation as it represents the object's dimensions in motion. A car is clearly not the same as a truck. And finally, we have the resistance coefficient or drag coefficient, which represents how aerodynamic a body is. For example, an airplane that is designed to be very aerodynamic has a resistance coefficient of about 0.03. A parachute, which is the exact opposite, as it is designed to generate a lot of resistance, has a coefficient of 1.75. In a falling motion on Earth, we have the force of weight going downwards, and we also have the friction force that opposes the weight. If you remember, the sum of forces equals mass times acceleration. In a world without air, the acceleration of a falling object would equal the acceleration of gravity. But once we factor in air's influence, that's no longer true. Now, the acceleration will be determined by how much larger the weight is than the resistance force. If the resistance is very small, the acceleration will be nearly identical to that of free fall. However, if the resistance is very large, there will be minimal acceleration. This is significant because the weight remains constant during free fall while the resistance varies. It depends on the speed, which means that in the first moments of movement, the resistance will be very small because the speed will also be. As a result of this, at the beginning of any fall, the movement will closely resemble the behavior in a free fall without friction. But as the seconds go by, the object's speed increases, causing the resistance to also increase. And the acceleration becomes less and less, until there comes a point where the speed is so great that the resistance equals the weight. That speed is known as terminal velocity and represents the maximum speed at which an object falls subjected to the force of its weight. In an environment with an atmosphere that slows it down. In a parachute jump, it takes about 5 seconds to reach terminal velocity. After the initial 5 seconds, you won't accelerate further. You'll fall rapidly, but at a constant speed. Now I repeat the initial question. 2 bottles, one empty and one full, which one hits the ground first? The correct answer is it depends. Since they are 2 identical bodies being thrown at the same time in the same place, they will generate the same friction. However, the weight is not the same, so when solving the sum of forces, we will get a greater acceleration. For the full jug, its speed will be greater, so it will reach the ground sooner. But if we throw them from a small height, they won't have time to accelerate much, and therefore the friction will be negligible, in both cases. They will behave as if in free fall. That's why from this low height, they fall simultaneously. However, if we greatly increase the height, the bodies will accelerate enough for the friction to act. Due to the bottle's light weight, a slight increase in aerodynamic resistance will significantly slow it down. So it can be clearly seen in the videos that the one with water reaches the ground first. A few weeks ago, I posted a survey on my Instagram account asking exactly this. In case I dropped 2 balls of different mass, but the same shape, which one would fall first? There were 3 possible answers. At the same time, the one with more mass will fall first, or it depends on the altitude. We have already seen that the correct answer will actually be the third one, because if I drop them from a small height, both will fall practically as if they were in a vacuum, that is, at the same time. But if the height were considerable, the resistance would increase a lot in the ball of little mass, and therefore, it would slow it down, making the heavier ball fall first. In the survey, the option that got the most votes was that both balls fell at the same time. Most who voted for that option likely believed the problem was assumed to be in a vacuum. Let's discuss that. The terminal velocity of an object depends on both its mass and shape, as the shape determines the cross-sectional area and friction coefficient in the equation. The clearest example is a person jumping from an airplane with a parachute. Initially, he carries it in his backpack. The cross-sectional area and the friction coefficient are determined by the person's body. However, when the parachute deploys, even though the mass remains the same as the friction, it suddenly increases a lot due to the parachute generating a lot of upward force that slows down the person who is falling. So, let's get to the question that led me to make this video. If we compare a free fall of 1 person with a free fall of 2 people tied together, the mass of the 2 people will be double. However, their cross-sectional area and resistance coefficient will be nearly identical. So when the individual person has reached their terminal velocity, the 2 people in tandem will still be accelerating more because the friction is still not equal to the weight. And this is the reason why the 2 people will fall faster. Their terminal velocity will be higher. And if it weren't for the addition of a small parachute known as a jog to increase resistance, wouldn't 2 people fall at the same speed as 1? In case anyone doubts, I did a tandem jump with an instructor using a small parachute. We were falling at the same speed as the person who was right in front of me filming. If we hadn't deployed that small parachute, we would have fallen faster. So yes, for cases with friction, mass does matter in a free fall, but so does the cross-sectional area and the friction coefficient. Some people believe that objects in free fall in a vacuum will fall at the same rate, regardless of their mass. That's why, when I released my video and said that 2 people fall at a different speed than 1 person, we could see in the comments disrespectful, arrogant people, but who were also wrong. The serious thing is that if you go into this video and start looking at the comments, do you think about the person who made the video? In that case, I was wrong, because everyone in the comments said that the video was bad. And I don't know about you, but honestly I find it quite worrying. The 9th of October, 2012. Felix Baumgartner became one of the most famous people in the world by jumping from nearly 40,000 meters. Commercial airplanes typically fly at altitudes of approximately 10,000 to 11,000 miles. So he jumped from almost 4 times that height. What's incredible is that during his jump, Felix became the first person in the world to break the speed of sound with his own body. And in free fall, but how is this possible? Well, most normal parachute jumps are made from about 4,000 meters high. At such low altitudes, air density and resistance are very high, making the terminal speed relatively low, between about 200 and 400 kilometers per hour, depending on how you position your body. But at 40,000 meters, the air density is 300 times less than at sea level. By jumping, Felix accelerated until he exceeded the speed of sound. But as he descended, the density was increasing, and therefore the resistance would slow him down more and more. So if we compare a free fall between 2 exactly identical objects, that weigh exactly the same, dropping objects from the Empire State Building and 30 miles will result in different times to fall 218 yards. Again, this is due to air resistance. A few months ago, I was invited from Madrid Fly to fly in the wind tunnel, an incredible experience because they taught me more or less how to move in a free fall. This tunnel consists of a vertical duct in which the air rises at a tremendous speed to keep you still. This happens because the air rises at the terminal speed of your body, allowing me to feel the magic of aerodynamic forces. Because a simple variation of looking down or up with my face changed my cross-section a few square centimeters, causing my body to rise or fall. Because that gesture was changing my terminal speed, is that balance so fine? And of course, I was able to stretch out an arm which allowed me to turn 360 degrees, abruptly, incredible. An interesting thing is that the person who is helping me can stand on the net, because their terminal velocity when standing and having less cross-section is much higher. Which means that the air is not going fast enough to keep them flying. However, a person who is lying down does go at the terminal speed of the air, and that's why they can stay suspended. Here's an example from an expert so you can see the crazy things you can do if you know how to manipulate 100%. The aerodynamic forces, all of this would be completely impossible in a vacuum. Another important point is people who believe that when you throw a body upwards, it will then fall at the same speed that you threw it. Is this what high school teaches us? That's in a vacuum though. On Earth, where there is an atmosphere, the arrival speed is likely the terminal velocity. If you shoot into the air, the bullet's speed when it hits the ground will differ from its initial speed when fired from the gun. There are many other interesting experiments. Like if you put a sheet of paper right on top of a book and let it fall, the sheet will fall at the same speed as the book. Because it removes all friction from the sheet, which has a low weight and large cross-sectional area, resulting in a very low terminal velocity and slow descent. A single sheet, but as explained in the video, if this experiment was done in a vacuum, both would fall simultaneously. I hope you now fully understand free falls. If you have questions, put them in the comments, and remember that you have my book, The Manual to Think Like an Aerospace Engineer, that is rocking it to learn everything in a practical way. Thanks, and see you next video.